Fascinating problem from a number theory book all the way back, I think, in the 60s, maybe the 70s, something like that. But by composite here, I mean not prime, okay? Not prime. Meaning any composite number, for example, 8 has divisors between 1 and 8, namely 2 times 4 in the case of 8, okay? So by composite, I mean not prime, okay? Now, we had this guy way back when, I don't know if this is a French name, he claimed that one or both of numbers in this form were prime. Okay, this is way back in 1509 pre-calculator, okay? But notice that and you can see why he believed that. Notice this would be the n equals 1 case right here. This would be for n equals 1, right? 6n, 6 minus 1 is 5, and 6 plus 1 is 7. This would, of course, be n equals 2 right here. And all the way out here, what will we have? N equals 11. Now, the key aspect of this, which seems to support this gentleman's claim, is that these are both prime numbers. These are both prime numbers. This is prime. This is not prime. This is not prime. This is prime. This is not prime. That's prime, right? So it seems like this guy, this French guy, I guess, had a valid sort of claim. But it turns out it's a long ways from the truth. There's an infinite number of these types that are composite. Both of the numbers are composite, okay? So let's get busy showing that. Now, a lot of you guys might recognize this as the prime desert lemma right here. By prime desert, I mean you can create an arbitrary size sequence of natural numbers that are not prime, i.e. composite. So call it a prime desert. I don't know if you spell that with another S or something. We'll just leave it like this. I don't know. Okay. So this is the prime desert theorem. And if you take a look at the case K equals 6, K equals 6. Now you can kind of see why that would be the number of choice here, since we are talking multiples of 6 minus 1 and plus 1. When you get K equals 6, this very last term would be 7 factorial plus 7, right? No need to even know what 7 factorial is what's cool about this. Now the term preceding it would be, let me put a comma here. The term preceding it would be 7 factorial plus 6. Okay, and you can see this number is clearly divisible by 6 since 6 is a factor of 7 factorial, okay? And the one preceding it would be 7 factorial plus 5. And again, these are composite numbers because these are 3 consecutive composite numbers, right? 5 divides this number, 6 divides this number, and 7 divides this number. So we didn't have to take the entire sequence of numbers, just the last 3 meets our purposes. So this is clearly a multiple of 6. We'll call it 6n, right? See, that's cool, folks. You don't even have to calculate it to know that it's true. Okay, now that's just one case. Now this is one more than 6n, so this is 6n plus 1. Isn't this sweet? I think it's so cool. 6n plus 1 right here. And then right here, of course, 6n minus 1. Okay, so we have constructed 6n minus 1 and 6n plus 1 are both composite, right? These numbers are both composite, okay? And this alone refutes this guy's claim. He claimed that all of them were prime or one of them was prime, okay? And we've just shown that that part A here is false, okay? So this is false. We've just shown that part A is false. Okay, but they want to go a step further. Dudley wanted to go a step further. He said, show there are infinitely many such n such that blah, 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 right? Okay. Well, guess what we do there? The very same kind of thing would happen for k equals 7, right? K equals 7, 8, 9 ad infinitum. And y'all, that's very straightforward to see that, right? So this happens for the case k equals 6. The same kind of thing would happen for k equals 7, right? You would have 8 factorial plus 8, right? Or let's see. Or no, these would still be here, right? Or yeah, I'm sorry. If for 8 factorial, the very same kind of thing would happen, right? Just if you put 7 in here, well, let's just write it down. If for 7, what would we end up with right here? We would end up with the very last term would be 8 factorial. Now what we need, we don't need that actually. Sorry. Let me erase that. Okay. For k equals to 7. Let's see, what would we end up with, folks? The next to the last term would be 8 factorial plus 7, sorry. And y'all, that would be the next to the last term in this sequence, right? The last term would be 8 factorial plus 8. Now, but the term before this would be 8 factorial plus 6, right? I'm convincing myself as much as anything, folks. And then the one before would be 8 factorial plus 5, right? Now, that would be the case. In here, you got your 6n here, right? You have your 6n plus 1 here. And your 6n minus 1 here. And y'all, the same kind of thing would happen. Again, this is for 7. Same kind of thing would happen for 8, 9, and so on. So we've proved part C. Okay, this is infinite number of times. So we've actually proved this part B. Okay. So anyway, y'all, thought that was really, really neat. This prime desert result was the go-to thing, and I needed the hint. I could not figure out, even though it's like the basic result, kind of the classical result in number theory, I didn't think to use it. I saw it somewhere on the internet where somebody noticed this, that you could always get multiples of 6 and multiples of 6 plus 1 and 6n minus 1 consecutive in this sequence. It's obvious after you see it, but I never thought about it. I thought about this problem for a month, didn't even get close to figuring out why it was true. In fact, if you pick a random n, the chances are you're going to get a number in the form part A, which it was the mistake this guy made over 400 years ago. You know, if you pick just like, try 23, 24, any of them, you're almost always going to get 1 prime, okay? But this prime desert theorem result deals with super large numbers, right? We never even wrote down 7 factorial. 7 factorial is what, 5,040? So you see, it's no surprise that the French gentleman didn't think of this, right? Or thought he had a claim. Okay, so in any event, you had to pick a result, use a result with super, super large composite numbers to actually establish the veracity of part B. But anyway, I guess this at this point, you would write QED right here. And a little bit of hand waving is going on, but if you can construct that type of sequence for k equals 6, well, if you just back up 1, you'll have the same thing will happen for k equals 7 and so on, k equals 8. But anyway, y'all, I hope that was convincing. I love that problem quite a bit. Thank you for viewing.